Hi, my name is Hemang Chawla. I am pleased to present our work on crowdsourced 3D mapping, a combined multi-view geometry and self-supervised learning approach. This work was done along with Mati Jukola, Terence Browns, Ilahe Arani, and Behram Zonus. Autonomous driving and advanced driver-assistance systems utilize 3D semantic maps of road landmarks such as lane boundaries, stop lines, traffic signs and lights, and so on, describing their geometry. These maps are utilized for accurate planning and safe decision-making during the drive. However, creating such maps requires dedicated collection vehicles with sensors such as LiDAR, stereo cameras, inertial measurement units, wheel odometers, and so on. Therefore, regularly updating the map to reflect short-term changes due to road maintenance or long-term changes with urban planning is a highly costly endeavor. Crowdsourced mapping can provide an alternative solution to this challenge. By collecting crowdsourced data from vehicles such as taxis that drive around the city multiple times over the week, we can map the 3D positions of semantic road objects. In this work, we focus on the 3D positioning of traffic signs, given their importance in safe driving. Such a setup can use the easily available global positioning system and a monocular camera for updating the map. Our objective is to map the geodetic and camera frame coordinates of the traffic signs. However, this requires calibrating the camera, followed by depth or Ecomotion estimation to create the map. Previous works assume access to the camera setup, in which case the camera can be calibrated through checkerboard pattern-based calibration. Self-calibration approaches based on structure from motion to estimate the camera poses, scene structure, and camera intrinsics have also been proposed. Recently, self-supervised approaches that estimate the camera intrinsics within a multitask monocular framework have also been proposed. However, the utility of such approaches is yet to be analyzed and applied for the purpose of crowdsourced mapping. For Ecomotion estimation, SLAM-based approaches are popular. They predict accurate camera trajectories over long distances, especially with presence of loop closures. However, they suffer from tracking failure in case of limited features in the scene. Alternatively, the recently proposed self-supervised approaches predict the monocular depth and Ecomotion simultaneously. Their prediction of relative motion over short trajectories is highly accurate. They are also able to predict dense depth from single images. Yet their accuracy is limited to shorter distances. Hence, we hypothesize that combining the strengths of multi-view geometry and self-supervised learning approaches for camera calibration, depth, and Ecomotion estimation for crowdsourced mapping will lead to an increased map coverage. Here is our proposed framework. The input to the system is a set of n images and a corresponding set of GPS coordinates. Given the images and the GPS coordinates, we then perform camera self-calibration to extract the camera intrinsics, namely focal lengths and the principal point, which are unknown for crowdsourced data. We can utilize either the multi-view geometry or deep learning-based approaches for self-calibration. Here is an overview of the multi-view geometry-based self-calibration procedure. First, the GPS information is used to identify the portions of the image sequence where the vehicle is making a turn. The turns are necessary for calibration, as pure translation is a degenerate scenario with ambiguity between radial distortion and scene depth. We utilize the Ramer-Douglas-Baker algorithm to decimate the original GPS trajectory to identify the turns. As can be seen, each red point in the decimated trajectory corresponds to a portion where the car was making a turn. Thereafter, we reconstruct each turn using Colmap to estimate and optimize the camera parameters within an iterative structure from motion framework. Alternatively, self-supervised learning with view synthesis loss from adjacent frames in a video is used to predict the camera intrinsics. Here is an example of self-supervised learning of camera intrinsics from Gordon et al. The pose network that predicts the camera transform is also used to predict the intrinsics. Since camera intrinsics are predicted per image pair, we use the measure of central tendency such as median to obtain the final parameters for a video sequence. The images with known calibration are then used to perform Ecomotion estimation or depth estimation. Since monocular vision suffers from scale ambiguity, these are scaled and aligned with the GPS coordinates to output the camera poses or dense scene depths at metric scale. Depending upon whether the depth or Ecomotion is used, we propose two approaches to compute the traffic sign positions. In approach A, the camera intrinsics, the scaled camera poses, and the traffic sign detections in the images are used to triangulate the traffic sign positions. In this approach, we utilize orb slam to get the Ecomotion of the camera. However, this is not scaled or aligned to the real world. To do so, we utilize the GPS coordinates by first converting the latitude, longitude, and height to local coordinates using the Mercator projection. Thereafter, we use the Umayama's algorithm to scale and align the estimated trajectory with the GPS trajectory in local coordinates by minimizing the mean squared error between them. Finally, we triangulate and optimize the traffic sign positions by using the coordinates of the signs in the images, the scaled and aligned camera poses, and the camera intrinsics. In this process, the sign positions are initialized using the midpoint algorithm, followed by nonlinear bundle adjustment for refinement. Alternatively, in approach B, the camera intrinsics, the scaled dense depth maps, and the traffic sign positions in the images are used to compute the traffic sign positions. In this approach, we use monocular depth estimation from self-supervised networks such as monodepth2 or depth from videos in the wild to get the dense depth maps. Or the GPS coordinates are converted to local coordinates before being employed for depth scaling. As shown in the image, the relative translation predicted by the network and the relative translation from the GPS are used to compute the scaling factor for the depth maps. By matching the detections of the traffic signs in the images with the depth maps, we can compute the depth at the center of the traffic sign. Thereafter, applying inverse projective mapping on the traffic sign image coordinates and the predicted depth, we can compute the 3D positions of the traffic sign. Finally, once the traffic sign positions are determined, using either of the approaches, the intrinsics corresponding to the cameras of different vehicles, the trajectories of the vehicles, or the corresponding depth maps, and the estimated 3D traffic sign positions are stored within the mapping database. Now, to evaluate our proposed system of crowdsourced 3D traffic sign positioning with unknown cameras, we first study the sensitivity of the proposed system to the calibration accuracy. Thereafter, we note the performance of multi-view geometry and self-supervised approaches to self-calibration and depth and Ecomotion estimation. We study the impact of these components on the sign positioning accuracy to formulate the best way for combining their strengths to increase the map coverage. All our experiments are performed on the traffic signs found in the KITTI raw dataset, whose specifications we make publicly available. First, the sensitivity analysis. We observe that the 3D positioning performance improves with loop closure. More number of loops, as in sequence 5, leads to higher improvement when compared with the improvement corresponding to sequence 7 with only a single loop. We also note that the traffic sign positioning is more sensitive to underestimating the focal length. However, the sensitivity to varying the principal point is higher than the sensitivity to varying the focal length. Also, errors in estimating one parameter are compensated with the errors in other parameters in the opposite direction to minimize the reprojection error. Noting this, we analyze the primary steps of crowdsourced mapping, namely self-calibration and depth and Ecomotion estimation. First, comparing the multi-view geometry-based self-calibration through CallMap to the self-supervised calibration using videos in the wild. We note that CallMap performs better. However, when the turns are not present, for example in sequence 4 of KITTI, median camera parameters predicted by the network may be used instead. Comparing the Ecomotion and depth estimation approaches, we note that the Ecomotion with OrbSlam is better for full trajectories. Furthermore, loop closure improves the performance due to nonlinear bundle adjustment. However, OrbSlam fails tracking in the case of sequence 1 of KITTI and hence cannot be used. Instead, self-supervised depth maps based traffic sign positioning is preferred. The depth estimation with MonoDepth 2 is better when training on the single set of learned camera intrinsics rather than with videos in the wild, which simultaneously predicts the camera intrinsics. Knowing this, here is our framework for combining the strengths of multi-view geometry and self-supervised learning to tackle the scenarios where the alternative fails, thereby increasing the total map coverage. If the calibration is known beforehand, we proceed to compute the traffic sign positions. Else, we identify whether the sequence contains any turns. If no turns are present, deep learning-based self-calibration is used. Else, multi-view geometry-based approaches applied instead. For the 3D mapping, we first attempt OrbSlam-based Ecomotion estimation, which, if successful, outputs the traffic sign positions through approach A. However, if the SLAM trajectory tracking fails, monocular dense depth maps are computed to apply approach B for mapping the traffic sign positions. Our system achieves an average relative accuracy of 58 centimeters and average absolute accuracy of 1.54 meters when using the combined pipeline for 3D crowdsourced mapping of traffic signs on all sequences of KITTI. This corresponds to relative accuracy of 39 centimeters on all frames where the signs were observed and an absolute accuracy of 1.26 meters for all the signs. Thus, with our system, we are able to demonstrate accurate single-journey crowdsourced 3D traffic sign positioning from unknown cameras that benefits from the combination of multi-view geometry and deep learning components. As an example, here are some of the mapped traffic signs in Germany using our approach. Thank you.